At the center of our galaxy, there is something that should not be possible. It gives off almost no light. It does not shine like a star. It does not glow like a nebula. You cannot see it with your eyes, and for most of human history you could not see it with telescopes either. And yet, everything near it moves as if an invisible monster is sitting there, pulling on the heart of the Milky Way, with the mass of roughly 4 million suns. That object is Sagittarius A star, a supermassive black hole, not in some distant galaxy at the edge of the observable universe, not in a place so remote that it feels abstract, but here, in our own galaxy, at the very center of the stellar city we call home. That alone would be enough to make it one of the most extraordinary objects in astronomy. But Sagittarius A star is strange for another reason. It is quiet, not dead, not harmless, just quiet. Other supermassive black holes blaze like cosmic furnaces. They devour gas, shred stars, and light up the universe with jets and radiation so intense they can outshine entire galaxies. Sagittarius A star does almost none of that. It sits in the dark, it flickers, it stirs, it occasionally flares, but most of the time it behaves less like a raging beast and more like something ancient waiting. And that silence made it harder to find. For centuries, the center of the Milky Way was not just mysterious, it was hidden, buried behind thick curtains of dust, drowned in the glow of countless stars, concealed by the very galaxy it controlled. We were living inside a spiral galaxy with a black hole at its core, and yet we had no clear view of the things shaping our cosmic neighborhood. So how do you discover something that cannot be seen directly? How do you prove the existence of an object that swallows light? How do you photograph the edge of a darkness so deep that even reality begins to bend around it? That is the journey of Sagittarius A star. It is a story about invisible gravity, about instruments that had to become more powerful than anything astronomers had built before, about scientists tracking stars for decades just to watch them betray the presence of something hidden, and about one terrifying realization. The center of the Milky Way is not empty, it is occupied. What makes this story even stranger is that the deeper we go, the less Sagittarius A star behaves like the black holes people imagine. It does not constantly feed, it does not dominate the night sky, it does not announce itself with violence every day. Instead, it teaches us something more unsettling. Sometimes, the most powerful thing in a system is not the loudest. Sometimes, it is the thing everything else moves around. And that is exactly what Sagittarius A star is. Over the next journey, we are going to move from the outer glow of the Milky Way into its hidden core. We will trace the first strange radio whispers that came from the direction of Sagittarius. We will follow the stars that gave away the black hole's mass. We will step into the world of infrared astronomy, adaptive optics, and the Event Horizon Telescope. We will see how humanity photographed something that should have remained forever beyond sight. And then we will go further, because discovering Sagittarius A star was only the beginning. The real mystery is not just that a black hole lives at the center of our galaxy. The real mystery is what it is doing there, what it has done in the past, and what it may still do in the future. Because the heart of the Milky Way is not asleep in the way we once hoped. It is only quiet. And quiet things in the universe have a way of becoming terrifying when they finally speak. So before we can understand the black hole itself, we have to begin with the reason it stayed hidden for so long. The Milky Way did not simply contain the truth. It buried it. When people look up at the night sky from a dark enough place, they can see the Milky Way stretching overhead like a pale river of light. It looks soft, almost peaceful. A luminous band brushed across the darkness. But that glow is deceptive. What you are seeing is not mist. It is not cosmic smoke. It is not a celestial cloud. It is an immense concentration of stars, billions of them, packed into the disk of our galaxy, their light blending together until the sky seems to glow. And near the center of the Milky Way, that glow becomes thicker, brighter, denser. That is where the problem begins. Because the center of our galaxy does not come to us as a clean image. It comes tangled with dust, gas, confusion, and distance. Between Earth and the galactic center lie vast clouds of interstellar dust, tiny grains of carbon, ice, silicates, and other debris left behind by generations of stars. Individually, those particles are microscopic. Collectively, spread across tens of thousands of light years, they form a barrier. Visible light does not pass through that barrier easily. It scatters. It gets absorbed. It vanishes into the dark. So for centuries, when astronomers tried to look toward the center of the Milky Way, they were not seeing the truth. They were seeing a distortion, a crowded foreground, bright stars near us, thick dust lanes cutting through the view like smoke, a false wall between the observer and the galaxy's hidden core. This region is part of what astronomers call the galactic bulge, the dense, swollen central region of the Milky Way. Unlike the thin spiral disk, the bulge is packed with stars in all directions. It is one of the oldest, busiest, most chaotic parts of the galaxy. And from our position inside the Milky Way, looking toward that bulge is like trying to understand the layout of a city while standing inside a blizzard of headlights. You see light everywhere, but you do not see structure. That blindness shaped human understanding of the galaxy for a very long time. Early astronomers did not know about interstellar dust. They assumed that what they could see was roughly what existed. In the 18th and 19th centuries, scientists such as William Herschel tried to map the Milky Way by counting stars in different directions. It was a reasonable method for the time. More stars in one direction might mean the galaxy extends farther that way. Fewer stars might suggest an edge, but the method had a flaw hidden inside it. If dust blocks your view in one direction, then fewer visible stars do not mean fewer stars exist there. They simply mean you are blind in that direction. And the direction where our view was most badly blocked was the one that mattered most, the true center of the galaxy. For a while, that led to a strange illusion. Because astronomers could not see deep into the galactic center, some believed the sun might sit somewhere near the middle of the Milky Way. The stars seemed distributed all around us. The sky appeared roughly balanced. It was only later that we understood the symmetry was fake. Our view toward the real center was dimmed by dust, making the galaxy look less lopsided than it truly was. In reality, we are not near the center. We are far out in the disk, orbiting the galactic core from a distance of about 26,000 light-years. Which means for most of history, humanity was trying to understand the heart of its own galaxy from the side, through a storm, while blind to the most important region of all. And yet the center kept leaving hints, not optical hints, not things telescopes built like giant eyes could easily detect, but whispers in other forms of light. That was the breakthrough astronomy needed. The universe is not limited to visible light. Stars, gas, dust, plasma, and black holes all interact with a much larger spectrum: radio waves, infrared, X-rays, gamma rays. Once scientists realized the galactic center was hiding behind dust, the solution became clear. Do not keep staring harder with ordinary eyes. Build new eyes. Infrared light can pass through dust more effectively than visible light. Radio waves can travel through regions that look completely opaque in the optical sky. That meant the center of the Milky Way was not truly invisible. It was invisible only to the kinds of instruments humans had relied on for too long. And when those new instruments finally came online, the darkness began to break. Infrared telescopes revealed stars where there seemed to be empty voids. Radio telescopes detected strange sources near the galactic core, signals unlike anything from ordinary stars. The blank patch at the center of the Milky Way began turning into a place, then into a structure, then into a puzzle with gravity at its center. Because once astronomers could finally look through the dust, they discovered that the galactic bulge was not just hiding a crowd of stars. It was hiding motion. Fast motion. Tight motion. Motion around something invisible. But the first true crack in the wall came even before that, not from a giant observatory searching for black holes, but from an engineer trying to understand static. And without meaning to, he became the first person to hear the center of the Milky Way speak. In the early 1930s, Carl Jansky was not looking for the center of the Milky Way. He was looking for noise. Jansky worked at Bell Telephone Laboratories, where engineers were trying to improve long-distance radio communication. Radio was becoming more important, and one of the problems facing the technology was interference. Signals crackled. Static came and went. Some of it was clearly linked to thunderstorms. Some came from other earthly sources. But there was a stubborn background hiss that did not fit the usual explanations. So Jansky was given a task that sounded technical and ordinary. Find the source of the interference. To do it, he built a rotating radio antenna unlike anything most people had ever seen. It sat on wheels and turned slowly, scanning the sky in different directions. It was not built to discover the secrets of the universe. It was built to troubleshoot communication systems. But science often changes course when someone notices something strange and refuses to ignore it. As Jansky gathered more data, he found that some static followed weather patterns. That made sense. Lightning produces radio waves. Storms leave signatures in the air. But there was another signal that behaved differently. It rose and fell on a regular cycle. At first glance, it seemed close to a daily pattern. Then Jansky noticed the detail that changed everything. The signal returned about 4 minutes earlier each day. That slight offset mattered. A 4-minute shift is not what you expect if something is tied to the sun and Earth's normal day-night cycle. It is what you expect if something is fixed relative to the stars. In other words, the source was not local. It was not weather. It was not the sun. It was cosmic. The strongest part of the signal came from the direction of Sagittarius, toward the dense, central region of the Milky Way. For the first time in history, humanity had detected radio waves coming from beyond the solar system. Jansky had opened a new sense. He did not yet know he was helping begin the study of our galaxy's hidden center. He had found a signal, not a black hole, a whisper, not an explanation. But what mattered was that the universe had just spoken in a language astronomy had barely begun to understand. That language was radio. At first, the significance of the discovery was not fully appreciated. Traditional astronomy was still dominated by optical telescopes. The great observatories of the era were built around visible light. Radio seemed strange, indirect, almost secondary. Jansky's discovery was important, but it did not instantly transform the field. That came later. A few years after Jansky, another radio pioneer, Grote Reber, took the discovery seriously enough to build his own radio telescope in his backyard. Reber was not waiting for astronomy to catch up. He constructed a parabolic dish and began systematically scanning the sky, confirming that radio waves were indeed coming from celestial sources. His work helped create the first radio maps of the sky and turned a strange engineering anomaly into a new branch of astronomy. Suddenly, the universe looked different. Objects invisible to optical telescopes glowed in radio. Some regions dark in visible light were bright in radio wavelengths. Structures buried behind dust began to emerge. And, near the direction of Sagittarius, there was a particularly strong and compact source of radio emission. Astronomers eventually called the broader region Sagittarius A. At first, it was just another radio source. Bright. Interesting. Mysterious. But as instruments improved through the mid-20th century, scientists realized this source was not ordinary. It was compact, persistent, embedded in the galactic center. And there were signs that something powerful lay there. Still, the evidence was incomplete. A radio signal alone does not prove a black hole. It tells you something energetic exists. It hints at unusual conditions, but it does not give you mass, shape, or structure. For that, astronomers needed more than a signal. They needed resolution. They needed better telescopes, better wavelengths, and eventually a way to watch individual stars moving near the hidden source. Even so, the logic had begun to change. The center of the Milky Way was no longer a vague darkness. It was active. It was emitting. It was not just a blank, obscured region behind dust. Something was there. As radio astronomy matured in the 1940s, 50s, and 60s, more instruments came online, bigger arrays, better detectors, sharper maps. The central radio source in Sagittarius remained one of the most compelling targets. Astronomers could see gas clouds, remnants of stellar explosions, and dense activity near the core. They could also see that the compact source at the center was unusually concentrated. That concentration was a clue. If a signal comes from a large diffuse cloud, it spreads out. If it comes from a small region, especially one buried deep in a violent environment, it suggests some kind of engine, a central driver, something dense enough, energetic enough, or extreme enough to dominate the region around it. By the 1970s, that central compact source was refined into what became known as Sagittarius A star. The name sounds almost casual, but what it represented was profound. A point-like radio source at the center of our galaxy, occupying the place where the Milky Way's gravitational heart ought to be. Still, even then, it remained a suspicion more than a final answer. The black hole had not yet been proven, because radio waves had done something extraordinary. They had revealed a hidden region behind the dust. But to understand what truly sat there, astronomers needed to see the stars buried inside the darkness. And for that, they would need a different kind of light, one that could slip past the dust and show the crowded core for what it really was. That is when infrared astronomy stopped being a useful tool and became the key. Visible light made the center of the Milky Way look blind. Infrared changed that. If radio astronomy was the first whisper from the hidden core, infrared astronomy was the moment the curtain began to lift. It did not make the dust disappear, but it allowed astronomers to see through enough of it that the heart of the galaxy could finally start taking shape. That mattered because the center of the Milky Way is not empty. It is crowded beyond ordinary imagination. Stars pile over stars. Gas clouds overlap. Ancient stellar populations mix with younger, hotter objects. Energy moves through the region in ways that are easy to miss when all you see is darkness and scatter. Infrared light travels more effectively through dust than visible light does. That one physical fact changed everything. Regions of space that looked black in optical telescopes turned bright in infrared. Star clusters hidden behind veils of dust began to emerge. Structures inside the galactic bulge could finally be mapped with increasing clarity. The center was no longer just inferred from radio emissions. It was becoming a place astronomers could study more directly. But this was not easy. Infrared astronomy comes with its own challenges. Earth's atmosphere absorbs much of the infrared light coming from space. The atmosphere also glows with heat, creating a noisy background that can swamp faint cosmic signals. So if you want a better view in infrared, you need to climb higher, where the air is thinner, drier, and colder. That is why some of the great infrared observatories were built on remote mountaintops and in high deserts. Places like Hawaii and the Atacama Desert in Chile became gateways to buried parts of the universe. And from those places, astronomers began to peer toward the center of the Milky Way with instruments that could do what optical telescopes never could. They could separate the hidden stars from the dust. Suddenly, the galactic center came alive. There were stars there, not just a few, but dense swarms of them. The central region was not a dark void. It was a bustling stellar environment with motion, heat, and structure. The radio source in Sagittarius was sitting inside a real astrophysical arena. And the more clearly astronomers saw that arena, the more one question became unavoidable. What exactly were all these stars moving around? Space-based infrared telescopes pushed the field even further. In 1983, the Infrared Astronomical Satellite, or IRAs, mapped the sky in infrared and showed just how much the dusty universe had been hiding. Later missions, especially the Spitzer Space Telescope, added far more detail. Spitzer could see warm dust, dense star fields, and emission from regions buried behind optical obscuration. It did not just help study the galactic center. It transformed how astronomers understood the hidden universe as a whole, and the Milky Way's center was one of its most compelling targets. Meanwhile, ground-based observatories kept improving, and one technological leap became especially important: adaptive optics. Normally, Earth's atmosphere blurs starlight. The stars appear to shimmer because turbulent air bends light in constantly changing ways. To the human eye, that shimmer looks beautiful. To astronomers trying to track tiny motions near a black hole, it is a disaster. Adaptive optics changed the game by allowing telescopes to correct for atmospheric distortion in real time. Mirrors could shift rapidly, hundreds or even thousands of times per second, compensating for the atmosphere's blurring effect. The result was a much sharper image of the galactic center than had ever been possible from the ground. Now astronomers could do more than just see that stars were there. They could track them. That was the turning point. Because a hidden mass does not need to emit light to reveal itself. If it is heavy enough, gravity will do the talking. Watch the stars long enough, and their motion becomes testimony. The key was patience. Not hours, not days, years, decades. In the dense region around Sagittarius A star, some stars move at incredible speeds. They whip through tight orbits around a central point, as if held by something both compact and immensely massive. Those motions are not vague patterns. They are measurable paths. If you can follow a star long enough to see its orbit, you can calculate the mass of the object controlling it. That was the opportunity infrared astronomy created. It opened the door to the center of the galaxy, but it also opened the door to a new method of proof. No longer would the black hole have to be guessed from radio emissions or broad theoretical expectations. It could be weighed through the dance of the stars themselves. And once that work began in earnest, the evidence became almost impossible to escape. Because the stars nearest Sagittarius A star were not drifting gently through a crowded sky. They were racing, and the faster they moved, the worse the implication became. There are only so many things in the universe that can make stars move like that. A dense star cluster could not explain the tight concentration of mass. A cloud of dark objects would not remain stable enough. A luminous source was absent. The list of possibilities kept shrinking. Something invisible was sitting there, with a grip strong enough to bend entire orbits. Something compact enough that millions of solar masses were packed into a region smaller than our solar system. And that conclusion did not come from one observation. It came from watching the same stars again and again and again, year after year, until the truth became undeniable. The dust had hidden the center of the galaxy. Infrared gave us the first real view inside. But it was the stars themselves that finally gave the secret away. Black holes do not need to be seen to be exposed. They can be betrayed by what orbits them. That is exactly what happened at the center of the Milky Way. Once infrared telescopes and adaptive optics made it possible to resolve individual stars near Sagittarius A star, astronomers began one of the most patient and important investigations in modern astrophysics. They tracked the positions of stars in the galactic center with exquisite precision, not for days or weeks, but for years. Two teams became especially central to this effort. One, led by Reinhard Genzel, used the European Southern Observatories facilities. The other, led by Andrea Ghez, used the Keck Observatory in Hawaii. Working independently, on opposite sides of the world, both teams were trying to answer the same question. What is sitting at the center of our galaxy? The stars nearest Sagittarius A star were the key. These stars, often called S-stars, move in a region where gravity is extreme. Their orbits are fast, tight, and highly revealing. Among them, one star became famous, S2. S2 is not special because it is the biggest star in the region, or the brightest in the whole galaxy. It is special because its orbit is short enough and close enough to the central mass that astronomers could watch it complete a full path. Roughly every 16 years, S2 swings around the hidden object at the galactic center on a highly elongated orbit. That is astonishing. For a star to move that quickly around a central object, the thing at the center must be incredibly massive. But not just massive, compact. The mass cannot be spread out over a huge volume, or the orbit would behave differently. The more precisely astronomers mapped S2's path, the more the possibilities narrowed. At its closest approach, S2 rushes through the intergalactic center at thousands of kilometers per second. It moves so fast because the gravitational well is so deep. A star does not achieve that speed unless something enormous is pulling on it. By measuring the orbit, astronomers could calculate the mass causing the motion. The answer was staggering. The central object held about 4 million times the mass of the Sun, and it was confined to an incredibly small region. That combination is devastating to ordinary explanations. Could it be a dense cluster of dark stars? Not stable enough. Could it be a swarm of neutron stars or stellar black holes? Over time, such a cluster would collapse, disperse, or reveal itself in other ways. Could it be some luminous object hidden behind dust? No. There was not enough light, and the required concentration of mass was too extreme. One explanation survived: a supermassive black hole. This was one of the most elegant cases in astronomy, where motion became evidence. No one had to cross the galaxy. No probe had to descend into the core. The stars themselves were acting like test particles in a gravitational experiment. Their orbits contained the answer, and as more stars were tracked, the picture only became stronger. Some orbits were longer. Some stars passed farther out. Others came closer. All of them told the same story. There was a dominant mass at the center, invisible, concentrated, and far too compact to be anything but a black hole. Then came something even more remarkable. The motion of the stars did not just confirm a black hole in the broad Newtonian sense. It also began to reveal effects predicted by Einstein's general relativity. Near a supermassive black hole, space and time do not behave the way they do in ordinary environments. Gravity is not just a force between objects. It is curvature in space-time itself. As S2 swung through the deepest part of its orbit, astronomers detected relativistic effects in its motion and in the light coming from the star. That meant the black hole was not just a convenient label, it was a relativistic reality. Space was curved there, time was affected there. Einstein was right there. This was one of the reasons the work mattered so much. Sagittarius A star was not just the nearest supermassive black hole, it was also a laboratory. A place where humanity could test gravity in one of the most extreme accessible environments in the galaxy. And that changed the emotional scale of the story. Before the stellar orbits were measured, Sagittarius A star was a suspicious radio source. A likely candidate, a hidden engine. But once the orbits were mapped, once S2 completed its path, once the mass estimate settled and the compactness became unavoidable, the galactic center stopped being a mystery in the loose sense. It became a fact. There is a supermassive black hole at the center of the Milky Way. That statement sounds almost ordinary now because we have repeated it so often. But its implications are enormous. It means our galaxy is organized around an invisible gravitational anchor. It means the stars in the innermost region of the Milky Way are circling a point of darkness. It means the heart of our galaxy is not a bright cluster or a simple center of balance. It is an abyss, and yet the black hole remained unseen. That is one of the strange psychological effects of this story. By the early 21st century, the evidence was already overwhelming. Astronomers had watched real stars moving in real time around a dark mass. They had weighed it. They had constrained its size. They had seen relativity at work near it. And still, the black hole itself had not been imaged directly. We knew it was there the same way you know a predator is in the dark. If you can hear the footsteps, see the shadows move, and watch everything around it react with terror, the environment had given it away. But the creature itself was still hidden. That gap between certainty and sight became one of the next great challenges in astronomy. Because proving a black hole by its effects is one thing. Photographing the edge of one, that is something else entirely. But before humanity could do that, a deeper question emerged. If Sagittarius A star was real, then maybe the Milky Way was not unusual at all. Maybe a hidden monster at the center was not the exception. Maybe it was the rule. By the time the stellar orbits around Sagittarius A star had been tracked with high precision, astronomy crossed a threshold. The center of the Milky Way was no longer a question of vague suspicion. It was a place with numbers attached to it. A location, a mass, a scale, a gravitational profile. And those numbers were terrifying. Roughly 4 million solar masses, packed into a region smaller than our solar system. That is the kind of statement that sounds abstract until you force yourself to picture it. 4 million suns do not simply make for a heavy object. They make for a profound collapse of ordinary intuition. The Sun itself is massive enough to dominate the entire solar system. Multiply that by millions, then squeeze the result into a volume so compact that no ordinary star cluster, gas cloud, or conventional object could survive in that form. Whatever sat there had to be beyond the normal categories of astrophysics. A black hole was not just the best answer, it was the only one left standing. To understand why, it helps to think about what alternatives would have to accomplish. Suppose you tried to explain Sagittarius A star as a dense collection of dark stars, stellar remnants, neutron stars, or smaller black holes. Even if you could assemble such a cluster, it would be unstable on astronomical timescales. Objects would interact, scatter, merge, or collapse. The distribution would not remain quiet and compact enough to mimic the measured gravitational field indefinitely. Suppose instead you imagined a normal, luminous object hidden behind dust. That fails too. The required mass would produce enormous radiation in ways we do not observe. Dust can obscure light, but it cannot neatly erase all the signatures of a massive, conventional star-like object. Again and again, the alternatives broke apart. The black hole did not. And once the case became strong enough, Sagittarius A star joined a category of objects that had long lived at the intersection of theory and observation. Black holes had been predicted by general relativity, inferred from X-ray binaries, suspected in active galactic nuclei, and modeled as engines of quasars. But here, in our own galaxy, was something different. Not a distant abstraction, not a statistical argument, not a simulation. A real supermassive black hole close enough for us to study star by star. That proximity matters. Even though 26,000 light-years is a vast distance by human standards, it is relatively nearby on a galactic scale. Sagittarius A star became the nearest supermassive black hole we know of, and that turned it into a reference point, a benchmark, a place where theories of gravity, black hole feeding, stellar dynamics, and galactic structure could all be tested against an actual object. There was another profound implication hidden in this proof. If the Milky Way had a supermassive black hole at its center, what did that mean for galaxies in general? For some time, astronomers had already been studying active galaxies whose centers blazed with extraordinary energy. Quasars in particular were so bright that they could outshine the galaxies hosting them. The leading explanation was that matter was falling into supermassive black holes, heating up in accretion disks and releasing tremendous energy before disappearing beyond the event horizon. Those black holes were obvious because they were loud. Sagittarius A star was different. It was quiet, which meant the black hole itself was not broadcasting its presence through overwhelming luminosity. It had to be uncovered through gravity rather than spectacle. But once it was found, it fit into a larger and more unsettling pattern. Galaxies and supermassive black holes seemed to go together. This was not just a local curiosity. It suggested a deep connection between galaxy formation and black hole growth. Somehow, over cosmic history, galaxies had not merely tolerated these central monsters. They had evolved with them. That realization pushed Sagittarius A star into a much larger story. It was no longer just the hidden heart of the Milky Way. It was part of a universal architecture. But before we step into that bigger picture, it is worth lingering on one of the most unnerving parts of the Sagittarius A star discovery. The object is not simply massive. It is compact in a way that changes the meaning of space itself. A planet has a surface. A star has a photosphere. A gas cloud has an edge of sorts, however fuzzy. A black hole has none of those in the ordinary sense. What it has is an event horizon, a boundary not made of matter, but of consequence. Cross it and no signal returns. No light escapes. No outside observer can recover what went in. The black hole is not just an object. It is a region where causality gets trapped. That is what sits at the center of our galaxy. And the stars around it do not simply orbit a dark body. They orbit a place where the known laws of observation come to an end. The proof of Sagittarius A star, therefore, did something rare in science. It took a concept many people filed away as theoretical or exotic and anchored it to a real, measurable, nearby place in the sky. You can point to the constellation Sagittarius. You can track the stars near the galactic center. you can see their orbits, and from that motion you can infer the presence of an invisible giant whose existence changes the geometry of space-time around it. There are not many scientific ideas that move from mathematics to reality so cleanly and so dramatically. And still, the story was growing larger. Because once we knew the Milky Way had a black hole at its core, another question came into focus. Why stop at our galaxy? Maybe the real mystery was not why Sagittarius A star exists. Maybe the real mystery was why the universe seems to keep building things like it. Once astronomers accepted that Sagittarius A star is a supermassive black hole, the discovery immediately became part of a much bigger pattern. The Milky Way was not unique. Again and again, in galaxy after galaxy, astronomers found evidence that central black holes were not rare anomalies. They were common. In many cases, they were enormous. In some, they were violently active. In others, like our own, they were faint and quiet. But the deeper observations went, the harder it became to avoid one unsettling conclusion. A supermassive black hole at the center of a galaxy may be normal. That idea changes how you think about galaxies themselves. Most people imagine a galaxy as a grand collection of stars, gas, dust, and dark matter spread across cosmic space. That picture is true, but incomplete. At the center of many galaxies lies a gravitational anchor of astonishing scale, sometimes millions of solar masses, sometimes billions, a hidden engine that shapes the structure and evolution of everything around it. And that raises one of the most difficult questions in astronomy. Why? Why does the universe seem so eager to place these things at the centers of galaxies? Did the black holes form first, helping galaxies grow around them? Did galaxies form first, feeding their cores until black holes emerged? Or did both grow together in a kind of cosmic partnership? We do not yet know for sure, but there are clues. One of the most striking is the relationship between the mass of a galaxy's central black hole and the properties of the galaxy's bulge, the dense central concentration of stars. The bigger the bulge, in general, the more massive the black hole tends to be. That correlation suggests black hole growth and galaxy growth are not independent stories. They are linked. Somehow, over billions of years, galaxies and their central black holes appear to regulate one another. That is a shocking idea when you pause to think about it. A black hole is tiny compared to the full size of a galaxy. Sagittarius A star, for all its mass, occupies a region incredibly small relative to the Milky Way's full diameter. And yet central black holes may influence star formation, gas flow, galactic structure, and even the long-term fate of their host galaxies. In active galaxies, the mechanism is easier to imagine. Matter falls toward the central black hole, heats up, and releases enormous energy. That energy can drive winds and jets, pushing gas away from the core and affecting the raw material needed for future star formation. The black hole does not merely consume matter. It can reshape the environment of the galaxy itself. Sagittarius A star is much quieter today, but that does not mean it is irrelevant. It may simply be between active phases. Another mystery deepens the story. Astronomers have found quasars powered by black holes with masses of 1 billion suns or more, at times when the universe was still very young. That means some supermassive black holes grew extremely fast, far faster than simple models once suggested. Something in the early universe allowed these giants to emerge quickly. Maybe enormous clouds of gas collapsed directly into massive seeds. Maybe the first stars left behind unusually heavy black hole remnants. Maybe repeated mergers built them up at astonishing speed. Whatever the mechanism, it means supermassive black holes are not late decorative features of the cosmos. They are woven into the early history of structure itself. That makes Sagittarius A star more than a local curiosity. By studying the black hole in our own galaxy, astronomers gain insight into a universal problem. We cannot travel to the centers of distant quasars. We cannot track individual stars near every remote black hole with the same detail. But Sagittarius A star is close enough for detailed study, and that makes it a laboratory for questions that reach across the universe. It also changes how we interpret calmness. Because our black hole is relatively modest compared to the true monsters out there. The black hole in M87, for example, has a mass measured in billions of suns. Some of the largest known black holes, such as the one associated with Ton 618, are estimated in the tens of billions of solar masses. Compared to those giants, Sagittarius A star is almost restrained. But restrained is a dangerous word in this context. 4 million solar masses in one place is not small in any human sense. It only feels small when compared to even more outrageous cosmic extremes. And that comparison reveals something important. Size is only part of the story. Some black holes are bright because they are feeding heavily. Some are quiet because their surroundings provide little fuel. Some may be spinning rapidly, shaping their environment through relativistic effects. Others may be less active, more difficult to detect, more subtle in how they influence the galaxy around them. So when we ask why galaxies keep making these monsters, we are really asking several questions at once. How do black holes form? How do they grow? Why do they correlate with galactic bulges? Why are some galaxies violently active while others seem calm? And how much of a galaxy's visible history is actually controlled by something we can never see directly? There is no final answer yet. But there is a pattern. The Milky Way is not a galaxy that accidentally ended up with a black hole. It is a galaxy whose hidden center fits a deep cosmic rule. That realization does something subtle to the emotional tone of the story. At first, Sagittarius A star feels like a secret buried at the heart of our home galaxy. But once you zoom out, the secret becomes larger and stranger. The black hole at the center of the Milky Way is not the odd thing. The odd thing is that the universe seems to do this over and over again. It keeps building galaxies around darkness. And once you see that pattern, another question becomes unavoidable. If Sagittarius A star is only one member of a much larger family of supermassive black holes, then how does it compare to the true giants of the cosmos? And what does it mean that our own monster is quiet? There is something almost insulting about how calm Sagittarius A star appears. A supermassive black hole sits at the center of the Milky Way, holding about 4 million solar masses, warping space-time, dominating the inner motions of the galactic core, and yet, most of the time, it barely glows. That is not what people expect from a black hole. Popular imagination tends to picture black holes as endlessly hungry cosmic vacuums, swallowing everything around them in a constant frenzy. Reality is stranger. Black holes are only dramatic when there is something available to fall in. Without fuel, even a black hole of extraordinary mass can appear subdued. And that is exactly the puzzle with Sagittarius A star. Compared to the blazing central engines of active galaxies, it is dim. Quasars pour out unimaginable amounts of energy as matter spirals inward, forming hot, bright accretion disks that can outshine all the stars in the host galaxy combined. Sagittarius A star does nothing like that today. Its emissions are weak by black hole standards. It produces radio waves, infrared flickers, occasional X-ray flares, but not the overwhelming luminosity of a fully active galactic nucleus. In cosmic terms, it is fasting. That quietness was one reason it remained hidden for so long. If Sagittarius A star were feeding like a quasar, the center of the Milky Way would be one of the most obvious and violent regions in the sky. We might have inferred its presence much earlier. Instead, the black hole gives off only a faint signature, forcing astronomers to assemble the case through patience, multi-wavelength observations, and the motion of nearby stars. But the quietness also makes Sagittarius A star scientifically precious, because when a black hole is not drowning its environment in overwhelming brightness, astronomers can study the region around it in finer detail. They can watch nearby stars. They can measure faint flares. They can try to understand how matter behaves when the feeding rate is low. In a sense, the silence that made the black hole hard to discover is the same silence that now makes it one of the best laboratories for black hole physics. Still, silence invites suspicion. Why is it so quiet? Part of the answer seems to be supply. The central region of the Milky Way does contain stars, gas, and dust, but not enough material is currently flowing efficiently into the black hole to produce a brilliant accretion disk. Matter near Sagittarius A star can be heated, scattered, blown outward by winds, or trapped in turbulent patterns that prevent it from falling straight in. Only a small fraction of the available material actually reaches the event horizon. In other words, the black hole is not weak, it is underfed. That distinction matters. If the environment around Sagittarius A star changed, its behavior could change too. A sufficiently dense gas cloud wandering too close, a disrupted star, or a larger-scale inflow of matter could temporarily wake it up. The black hole's quietness is not a guarantee of permanent calm. It is simply the current state of the system. And there are hints that the current state may not reflect the past. Astronomers have found evidence suggesting that Sagittarius A star may have been far more active before. Structures known as the Fermi bubbles rise above and below the plane of the Milky Way, enormous lobes of high-energy emission that may preserve the aftermath of an energetic episode in the galactic center millions of years ago. X-ray echoes in nearby gas clouds also hint that the black hole may have flared much more brightly in the recent past, at least in astronomical terms. If those interpretations are correct, then Sagittarius A star is not truly a passive object. It is a quiet giant with a history, and that history makes its current stillness feel less reassuring. It is one thing for a black hole to be inactive because it has always been inactive. It is another for it to be quiet now because it is between phases. That second possibility carries a different emotional weight. It suggests that the Milky Way's center may not be stable in the simple, permanent way people like to imagine. It may simply be in a lull. There is also something psychologically disturbing about how little the black hole needs to remain terrifying. Even at low activity, the gravity near Sagittarius A star is immense. The region just outside the event horizon is still one of the most extreme environments accessible to study in the galaxy. Plasma there reaches extraordinary temperatures. Magnetic fields twist and tangle. Matter orbits at relativistic speeds. The system may look calm from a distance, but near the black hole itself, calm is the wrong word. The better word is restrained. And restrained things often feel more dangerous than openly violent ones, because they suggest hidden capacity. That is why Sagittarius A star remains so compelling. It is not merely a giant black hole. It is a giant black hole that refuses to behave in the simplest possible way. It does not make the story easy. It forces astronomers to ask harder questions about black hole feeding, magnetic turbulence, episodic activity, and the long-term rhythms of galactic centers. If it were brighter, the mystery might in some ways be simpler. Instead, we are left with a more unsettling picture. At the center of our galaxy sits a predator powerful enough to control the motions of stars, yet quiet enough to hide in plain sight. And when something that powerful refuses to reveal all of itself, the next question is inevitable. If Sagittarius A star is underfed, where is the bright ring of falling matter we expect around a black hole? And why, in a system so quiet, do sudden flares still erupt without warning? When people imagine a black hole, they often picture a glowing whirlpool around it, a bright accretion disk, a furious ring of superheated matter spiraling inward, a beacon announcing the black hole's presence across space. In many active galaxies, that picture is justified. Matter falling toward a supermassive black hole can become so hot and luminous that the central region radiates with extraordinary power. The disk becomes the visible signature of the invisible engine. But Sagittarius A star does not present that image so cleanly. For a long time, astronomers looked toward the galactic center and found something far fainter than expected. There was emission, yes, radio waves, infrared activity, X-rays during flares, but not the brilliant, stable accretion disk of a fully feeding monster. At first, that seemed almost contradictory. The black hole was real. The mass was known. The crowded galactic center offered stars, gas, and dust. So where was the obvious disk? The answer appears to be that Sagittarius A star does have infalling material around it, but not in the dense, steady, luminous form seen in more active systems. Instead of a bright, thick accretion disk, the black hole seems to be surrounded by a hot, tenuous, chaotic flow. Much of the gas drifting inward heats up and swirls, but only a small fraction actually makes the final plunge. Some of it is pushed back outward by turbulence, pressure, or magnetic effects. Some remains too diffuse to radiate efficiently. The result is a system that is real, active, and dynamic, yet far dimmer than the classic image people expect. You might think of it like a fire trying to catch in thin air with scattered fuel. The ingredients are there, but not in the right concentration for a sustained blaze. That faintness, however, does not mean the environment near Sagittarius A star is uneventful. Every so often, the black hole produces flares, sudden bursts of brightness, brief surges in infrared or X-rays, moments when the quiet giant seems to twitch. These flares can appear with little warning. One moment, the region is dim. The next, it brightens dramatically, then fades again over minutes or hours. Their unpredictability is part of what makes them so valuable. Each flare is like a brief crack in the system's calm surface, a chance to glimpse the physics unfolding near the event horizon. What causes them? There are several possibilities, and the truth may involve more than one mechanism. One explanation is in falling clumps of gas. In a low-density environment, most of the material around Sagittarius A star is too sparse to produce strong emission. But if a denser pocket of gas drifts inward, it can heat rapidly as it approaches the black hole, releasing a burst of energy before crossing the point of no return. Another explanation involves magnetic reconnection. In plasma-rich environments, magnetic field lines can become twisted and stressed. When they suddenly snap and reconnect, they release energy explosively. On the Sun, magnetic reconnection drives solar flares. Near a black hole, the same basic process could produce far more extreme bursts. If that is what is happening near Sagittarius A star, then the flares are not just signs of feeding. They are signs of magnetic violence near one of the harshest environments in the galaxy. There are also more dramatic possibilities. A passing star could shed material. A compact object could disturb the flow. Something could be partially torn apart. In the crowded galactic center, close encounters are not impossible. But whether or not any single flare comes from such an event, the larger lesson is the same. Sagittarius A star is not inert. It is active in pulses, in fragments, in flashes. One especially striking flare in recent years drew significant attention because the black hole became much brighter than usual, raising questions about whether a new inflow of matter had reached the inner region. Events like that are reminders that the calm state of Sagittarius A star is never absolute. It can brighten, it can react, it can change. And those changes matter because they reveal the system's hidden machinery. The flares tend to come from very close to the black hole. Their rapid rise and fall imply a compact source, since only a relatively small region can vary on such short timescales. That points directly to the environment near the event horizon, where matter moves at a significant fraction of the speed of light, and where gravity, magnetism, and plasma turbulence all interact under extreme conditions. This is where the missing disk and the flares become part of the same story. The black hole is not surrounded by the kind of rich, luminous accretion structure seen in active quasars, because the inflow is weak and inefficient. But that inefficiency does not produce peace. It produces instability. A sparse system is not always a calm system. Sometimes it is a system balanced on the edge, where small changes can trigger sudden bursts. That makes Sagittarius A star feel less like a quiet lamp and more like a dying campfire that occasionally erupts when a pocket of fuel catches. And it leads naturally to another question. If the matter near Sagittarius A star is chaotic, patchy, hot, and unstable, what is organizing that chaos? Because gravity alone is not the whole answer. Close to the event horizon, another force is threading through the plasma, shaping the flow, storing energy, and perhaps deciding when the black hole glows and when it goes dark. Magnetism. And near Sagittarius A star, magnetism may be every bit as strange as gravity itself. Gravity is the main character in any black hole story. But near Sagittarius A star, Gravity does not act alone. Around the black hole sits a turbulent environment of hot plasma, charged particles, and distorted spacetime. In that environment, magnetic fields are not passive decorations. They may be one of the key forces controlling what matter does, how energy is released, and why the black hole often appears so dim despite its enormous mass. This is where the story becomes even stranger. When most people think of magnetism, they think of something orderly, a bar magnet, a compass needle, perhaps the invisible lines around Earth that guide charged particles near the poles. But the magnetic fields around a black hole are nothing like that. They are dragged by moving plasma, wound by orbital motion, stretched by turbulence, and distorted by relativistic gravity. They do not sit still. They twist, knot, reconnect, and sometimes explode. In some ways, they are like invisible weather patterns made of force. The plasma around Sagittarius A star carries magnetic fields with it. As the gas orbits the black hole, those field lines can become tangled and amplified. The faster the plasma moves and the more chaotic the flow becomes, the more complex the field structure can grow. Near the event horizon, where orbital speeds rise dramatically and gravity pulls hard on every particle, the magnetic environment can become extreme. This matters because magnetic fields can push back against gravity. Not completely, not enough to neutralize a black hole, but enough to shape how matter falls in. A simple picture of accretion makes it sound as though gas should spiral steadily into the hole, converting gravitational energy into heat and light. Real systems are more complicated. Magnetic fields can channel matter, slow it, redirect it, or help fling some of it back outward. They can act like brakes, barriers, or engines, depending on how the plasma is arranged. That may be part of why Sagittarius A star is so underluminous. If magnetic stresses and turbulent flows are preventing much of the gas from making a clean plunge inward, then the black hole's feeding rate remains low. Matter gets close, heats up, and then some of it escapes instead of crossing the horizon. The black hole's faintness, in other words, may be partly a magnetic story. But magnetism does more than suppress steady feeding. It also offers a powerful explanation for the flares. When magnetic field lines are twisted and compressed, they store energy. If those field lines suddenly reconnect, that stored energy can be released in a burst, accelerating particles and generating radiation. This process is known from other astrophysical systems, including the Sun. But near a black hole, the scale and conditions become far more extreme. A reconnection event near Sagittarius A star could light up the inner region in infrared or X-rays for a short time, then disappear as quickly as it came. That is one reason the flares feel so unpredictable. They may not require a large new mass of material to arrive. They may arise from energy already built into the magnetic geometry of the plasma itself. Recent observations, including polarized light measurements associated with Event Horizon telescope data, have given astronomers valuable clues about the magnetic structure near Sagittarius A star. Polarization tells us something about how electromagnetic waves are aligned as they leave the source, and in turn that reveals information about the magnetic field through which they traveled or from which they were emitted. The emerging picture suggests that the magnetic environment near Sagittarius A star is not random in the simplest sense. There may be organized structures close to the hole, perhaps more ordered than the chaotic outer flow would suggest. That tension between inner order and outer chaos is fascinating. It hints that the black hole's immediate environment might be a system hovering between stability and eruption. Strong enough to hold shape for a while, unstable enough to flare without warning. Magnetism also connects Sagittarius A star to the broader black hole population. In more active systems, powerful magnetic fields may help launch jets, those narrow beams of energetic particles that can shoot out across enormous distances. Sagittarius A star does not show the kind of giant, obvious jets seen in some active galaxies, but there are hints of weaker outflows. If those exist, magnetism is the likely driver. That would mean the black hole is not simply swallowing matter. It is interacting with its surroundings through an intricate balance of infall, turbulence, and release. This is one of the reasons black hole physics remains so difficult. A black hole itself, in the simplest theoretical sense, is described by only a few properties: mass, spin, and electric charge. But the environment around a real astrophysical black hole is not simple at all. Plasma physics, radiation transport, magnetic reconnection, turbulence, relativity, and geometry all collide in the same region. Sagittarius A star is therefore not just an object, it is a system where invisible magnetic structures may determine whether gas falls inward, whether a flare erupts, whether light escapes long enough for us to see it, and whether the whole region appears calm or unstable from one observation to the next. And all of this is happening close to the boundary beyond which no information escapes. That is what makes the next breakthrough so extraordinary. For years, we proved Sagittarius A star by radio waves, by infrared observations, by stellar orbits, by theory, and by gravity. But eventually, humanity attempted something even more audacious. It tried to look at the edge itself, not the singularity, not the black hole's interior, but the silhouette of the abyss, the darkest border in our galaxy. A black hole is, by definition, an object from which light cannot escape. So what does it mean to photograph one? The answer is subtle, and perhaps even more beautiful than a direct picture would have been. When astronomers image a black hole, they are not taking a normal photograph of a surface, because a black hole has no surface in the ordinary sense. They are capturing the glowing environment around it and, within that light, the shadow carved out by gravity itself. That shadow is what makes a black hole visible. Near the event horizon, light does not travel in straight lines. Space-time is curved so strongly that photons can be bent, captured, or redirected into strange paths. Some light from the hot material around the black hole reaches us after being warped around it. Some falls in and never returns. The result is a bright ring or crescent-like structure surrounding a dark central region, the black hole's shadow. That dark region is not the event horizon exactly. It is slightly larger, a silhouette shaped by the paths of light near the hole. But to see it is to see the gravitational presence of the black hole imprinted directly into the image. And for Sagittarius A star, seeing that shadow was unbelievably difficult. The problem begins with scale. Sagittarius A star is relatively close, which helps, but it is also much smaller than some of the giant black holes in other galaxies. On the sky, the shadow of Sagittarius A star appears astonishingly tiny, comparable to trying to resolve an object on the moon from Earth with absurd precision. Ordinary telescopes cannot do it. Even most advanced observatories cannot do it. To see something that small, astronomers needed a telescope the size of Earth. Not literally one structure, of course, but a network. A planet-scale observatory built by linking radio dishes across the globe using a technique called very long baseline interferometry. That network became the Event Horizon Telescope, or EHT. The EHT observes at millimeter wavelengths, which are short enough to provide extraordinary resolution, and can also penetrate much of the dust obscuring the galactic center. By combining data from observatories spread across continents, all synchronized with atomic clocks, the EHT effectively turns the planet into a single enormous instrument. It is one of the most ambitious imaging projects in the history of astronomy. In 2019, the EHT famously revealed the first image of a black hole's shadow, M87 star, the giant black hole in the galaxy Messier 87. That image was historic. It showed the world that black holes could move from theory and indirect evidence into something like sight. But Sagittarius A star was in some ways an even harder target. Why? Because the material near Sagittarius A star changes quickly. M87 star is vastly more massive, which means the timescales near its event horizon are slower from our observational point of view. Sagittarius A star, being far smaller, evolves more rapidly. Matter whirling around it can change the brightness pattern on timescales of minutes. Trying to image it is like taking a long-exposure photograph of something that refuses to hold still. That made the data analysis profoundly difficult. Astronomers could not simply take one clean snapshot. They had to combine huge amounts of information, average over changing structures, and extract a stable signature from a system flickering near the edge of causality. Years of work went into processing the observations. And then, in 2022, humanity finally saw it. A bright ring. A dark center. The shadow of Sagittarius A star. Blurry, yes. Not a cinematic science fiction image. Not a crisp edge you could trace with your finger. But unmistakable. A real image of the shadow cast by the supermassive black hole at the center of our galaxy. That moment carried a strange kind of power. We had already known Sagittarius A star was there. The stellar orbits had proved it. But seeing the shadow was different. It compressed decades of theory, instrument building, observation, data analysis, and human persistence into a single visual fact. The abyss had a shape, and its size matched expectations. The observed ring was consistent with a black hole of roughly the mass inferred from the orbits of nearby stars and from general relativity. This agreement mattered. It was not merely a pretty confirmation. It was a deep consistency check. Different methods, different physics, different kinds of evidence, all pointed to the same object. Gravity had told us it was there. Light had now shown us its outline. There is something philosophically haunting about that. A black hole is often described as the ultimate unseen thing. Yet what we eventually captured was not the hole itself, but the way it edits reality around it. The black hole becomes visible only by what it prevents us from seeing. It announces itself as absence, a darkness inside light, a missing center. That is almost too perfect for the object at the center of the Milky Way. The shadow of Sagittarius A star is not just an astronomical image. It is a statement about the limits of observation. There is a boundary beyond which the universe refuses to report back. We can approach it with equations, with telescopes, with inference and computation. We can study the plasma outside. We can map the orbits of stars. We can image the shadow. But beyond the event horizon, the story disappears from the outside universe. That is what makes black holes unique among astrophysical objects. They are not just difficult to observe. They impose a fundamental wall on what can be observed, and yet humanity still reached the edge. Which makes the next question even more extraordinary. How did we build the tools capable of doing that? Because the discovery of Sagittarius A star was not one moment. It was a century-long technological climb from static on a radio antenna to an Earth-sized telescope. And every step of that climb was a victory over blindness. The story of Sagittarius A star is not only a story about a black hole. It is a story about human instruments becoming strange enough, precise enough, and stubborn enough to catch up with reality. At every stage, the center of the Milky Way forced astronomy to evolve. Optical telescopes failed because dust blocked the view, so radio astronomy was born into relevance. Carl Jansky heard the first cosmic hiss from the direction of Sagittarius. Grote Reber mapped the radio sky. New arrays sharpened the view of the galactic center and isolated compact sources within it. That was the first victory. Then, radio alone was not enough. A signal could indicate something unusual, but it could not reveal the crowded stellar environment with the detail astronomers needed. So infrared astronomy rose to prominence. Mountaintop observatories and space telescopes opened new windows through the dust. What had looked like obscured emptiness became a vibrant, crowded core. Hidden stars emerged. Structure appeared where there had seemed to be only darkness. That was the second victory. Then even infrared images were blurred by Earth's atmosphere. The stars shimmered. Tiny motions near the galactic center were lost in turbulence. So astronomers developed adaptive optics, systems that could correct atmospheric distortion in real time by reshaping mirrors over and over again. Suddenly, ground-based telescopes could resolve the inner galactic center with unprecedented sharpness. That was the third victory. And with that precision came the stellar orbits. The work of Genzel, Ghez, and their teams transformed the black hole from a suspicion into a measured reality. S2 and the other S stars traced paths that weighed the invisible object. Gravity became evidence. General relativity became testable in our own galactic backyard. That was the fourth victory. But still, the black hole itself remained unseen, so astronomy kept climbing. X-ray observatories like Chandra helped reveal flares from the region, proving the core was not entirely dormant. Space telescopes such as Spitzer mapped the warm dust and infrared structures surrounding the center. Facilities working in submillimeter wavelengths, including arrays in high, dry locations, explored the hot plasma close to the black hole's immediate environment. Each wavelength added another layer to the portrait. And then came the most radical leap of all. If no single telescope on Earth could resolve the shadow of Sagittarius A star, then build a telescope using the Earth itself. That idea sounds impossible until you understand the logic of interferometry. If widely separated telescopes observe the same source at the same time, and their data are combined precisely, the separation between them acts like the diameter of a much larger virtual telescope. Increase the separation enough, synchronize the clocks tightly enough, record the signal accurately enough, and the resolving power becomes extraordinary. This was the foundation of very long baseline interferometry. The Event Horizon Telescope took that concept to its extreme. Observatories across the globe participated. Sites in North America, South America, Europe, Hawaii, the South Pole, and elsewhere observed simultaneously at millimeter wavelengths. The data recorded at each station were so vast and so timing sensitive that they had to be stamped with atomic clock precision and later brought together for correlation and analysis. This is not ordinary astronomy. It is planetary scale coordination. It is astrophysics fused with precision engineering, high-performance computing, atmospheric modeling, and algorithmic reconstruction. It is one of the few scientific endeavors where geography itself becomes part of the instrument. And even that was not enough to make Sagittarius A star easy. The atmosphere at each observing site had to cooperate. The source itself varied rapidly. Interstellar scattering blurred the signal. The data volume was enormous. The reconstruction process required not just gathering information, but deciding how to turn fragmented measurements into a trustworthy image without fooling ourselves. That last point is easy to overlook. When you image something at the limit of what is observable, there is a danger of seeing what you hope to see. So the EHT teams used multiple independent methods, cross-checks, simulations, and careful validation. The result was not a casual picture. It was a hard-won consensus, extracted from one of the most difficult astronomical datasets ever assembled. And when the image of Sagittarius A star's shadow was finally revealed, it carried all of that invisible labor with it. Behind that ring of light stood decades of human effort. Engineers who built detectors sensitive enough to work at the limits of signal. Observers who endured hostile conditions on mountaintops and in polar cold. Computer scientists who handled staggering datasets. Theorists who modeled what a black hole's shadow should look like. Astronomers who spent years watching stars drift through tiny arcs of sky. What the public saw as one image was, in truth, the tip of a century-long climb. That is what makes Sagittarius A star such a powerful scientific story. It is not just that the object is extreme. It is that it pushed humanity to expand its senses. The black hole did not become easier to see. We became more capable of seeing the universe. And that transformation is still underway. The next generation of instruments promises sharper images, better polarization mapping, more sensitive infrared monitoring, and perhaps even movies of plasma moving near the event horizon. Future observations may reveal the spin of Sagittarius A star more clearly, resolve flare structures with greater confidence, or tighten the connection between magnetic geometry and emission patterns. But even now, one truth is unavoidable. Humanity has seen the shadow of the black hole at the center of its own galaxy. That is already one of the most extraordinary sentences our species can say. And yet, even with all of that knowledge, one deeply unsettling possibility remains. What if Sagittarius A star is not finished? What if the quiet giant at the heart of the Milky Way is only resting between meals? A black hole does not need to be active all the time to be dangerous. It only needs fuel. That is why the future of Sagittarius A star remains one of the most intriguing questions in galactic astronomy. Today, our black hole appears subdued. It feeds weakly. It flickers. It produces occasional flares. But nothing in the laws of physics says it must stay that way forever. Galaxies evolve over enormous spans of time. Gas moves. Stars drift. Clouds collide. Orbits change. A system that looks stable on human timescales may be slowly setting up the conditions for a very different future. And there are several ways Sagittarius A star could become more active. The simplest is an increase in local fuel. If a denser gas cloud were to pass close enough to the black hole, tidal forces and friction could feed material inward. If a star wandered too near, part of it could be stripped away, or, in a more extreme event, destroyed. If stellar winds from the crowded central region combine differently, the inflow rate could rise. Each of these possibilities would turn the black hole brighter, at least temporarily. Astronomers saw a hint of this tension when a dusty object known as G2 approached Sagittarius A star. For a while, some expected fireworks. If G2 were a gas cloud, the close passage might feed the black hole and trigger a significant brightening. The outcome turned out to be less dramatic than some predictions suggested, possibly because G2 contained a star, or because the gas was not delivered efficiently into the hole. But the episode was important for a different reason. It reminded everyone that the center of the Milky Way is dynamic. Things are moving there. Close approaches happen there. The question is not whether the environment changes. The question is, how much change is needed before the black hole responds in a major way? There is also stronger evidence that Sagittarius A star has not always been as quiet as it is now. Large-scale structures like the Fermi bubbles suggest that the galactic center may have experienced a more energetic phase in the past. X-ray reflections in nearby gas clouds hint that the black hole may have shone more brightly a few hundred years ago than it does today. These clues do not imply a full quasar-like outburst in recent history, but they support the idea that Sagittarius A star is capable of much greater activity than its current dim state suggests. That makes the present moment feel provisional, not permanent, not guaranteed, just current. And if you zoom far enough into the future, the stakes rise again. Billions of years from now, the Milky Way and the Andromeda Galaxy are expected to merge. The stars themselves will mostly pass one another without direct collisions, because space is vast. But the gas and dust in the two galaxies will be violently stirred. Large amounts of matter could be funneled toward the merged galactic center. If that happens, Sagittarius A star, or whatever black hole exists at the center of the eventual merged system, could receive a major new supply of fuel. That could trigger a far more active phase, perhaps not tomorrow, not in human history. But in the long life of galaxies, these transitions matter. A supermassive black hole that is quiet now can blaze later. That possibility changes how we should think about the Milky Way itself. Our galaxy often feels serene in the imagination, a majestic spiral of stars rotating through the dark. But the truth is more restless. Galaxies are not frozen objects. They collide, feed, grow, and rearrange themselves. Their central black holes participate in that evolution. If Sagittarius A star entered a true active phase, the visual character of the galactic center would change dramatically. It could brighten enormously in high-energy wavelengths. Outflows or jets might emerge depending on the geometry of the magnetic fields and accretion flow. The inner galaxy could be flooded with radiation far beyond current levels. Earth would likely remain too far away for catastrophic immediate effects in most plausible scenarios, but the Milky Way would no longer look like the quiet spiral we know. The heart of the galaxy would announce itself, and there is something profoundly eerie about that. Right now, most people can live their whole lives without thinking about Sagittarius A star. The black hole shapes the inner galaxy but does not dominate the sky. It is there, yet hidden, important, yet visually absent. A perfect cosmic secret. But that secrecy may be temporary on long enough timescales. A feeding event, a denser inflow, a galactic merger, a new cycle of activity. Any of those could alter the story. This does not mean we should fear a sudden doomsday from the galactic center. Astronomy is not a horror movie in the childish sense. The relevant processes are mostly vast, gradual, and governed by orbital dynamics rather than sudden cinematic violence. But there is a deeper kind of unease here, one rooted in scale. Our galaxy feels permanent because our lives are short. Sagittarius A star does not operate on human time. It operates on galactic time, and in galactic time, even long periods of silence may simply be pauses between events. That is why Sagittarius A star matters beyond the thrill of black hole imagery or the elegance of stellar orbits. It is the central reminder that the Milky Way is not a static home. It is an evolving system with a hidden engine, a system whose most powerful object is currently quiet, but not necessarily tame. Which leads to the final and perhaps deepest reflection. After all the radio signals, the infrared images, the stellar orbits, the shadow, the flares, the magnetic chaos, and the possibility of future awakening, what does Sagittarius A star actually mean for us? What do we do with the fact that the center of our galaxy is not light, but an abyss? Part 14. The Silent Heart of Our Galaxy. The story of Sagittarius A star begins in darkness, not because the black hole is simple, but because the truth was hidden. Dust hid the galactic center. Distance hid its scale. Silence hid its power. And for a long time, our own galaxy concealed the thing at its core from the species living inside it. But piece by piece, that concealment failed. A radio hiss from Sagittarius suggested that something unusual was there. Infrared telescopes opened the first clear windows through the dust. Adaptive optics sharpened the stars. Decades of patient measurements revealed those stars whipping around an invisible mass. General relativity described the warped spacetime surrounding it. The Event Horizon Telescope finally gave us the shadow, the dark absence inside a ring of bent light. And what stood revealed at the end of all that work was not a shining center, not a cosmic beacon, not a throne of stars. It was a black hole. A supermassive black hole, roughly 4 million times the mass of the Sun, quiet most of the time, restless when watched closely, hidden at the heart of the Milky Way. There is something almost poetic about the fact that the center of our galaxy is defined not by what shines most brightly, but by what light cannot escape. In human stories, the center of a kingdom is usually a palace, a fire, a sunlit place from which order radiates outward. But the center of the Milky Way is the opposite. It is a darkness so deep that space-time bends inward around it. A place where stars race in obedience. A place we only learn to see by building instruments that could detect the universe far beyond what our eyes were ever meant to handle. That should humble us. Because Sagittarius A star is not just a scientific object, it is a reminder of how limited ordinary perception is. For most of history, we lived inside a galaxy without understanding its structure. We looked toward its brightest band and did not know what sat at the center. We mistook blindness for knowledge. We thought what we could see was the universe itself. It was not. The universe was wider in wavelength, deeper in structure, and stranger in design than human senses could reveal. Only when we extended those senses through technology did the Milky Way begin to tell us the truth. And the truth turned out to be unsettling. At the heart of our home galaxy is a region where the usual categories of experience break down. Space and time do not behave normally there. Matter heats, swirls, and vanishes there. Magnetic fields knot into violent patterns there. Light itself can orbit, bend, or die there. It is one of the few places in the accessible cosmos where our best theories of gravity confront the most extreme natural conditions we can observe. That is what the center of our galaxy really is. Not a symbol, not a myth, a relativistic abyss. And yet, even after all we have learned, Sagittarius A star remains incomplete as a story. We do not know every detail of how supermassive black holes form. We do not know exactly how the earliest giants grew so fast. We do not know how often our own black hole changes states, how strongly it may have shaped the Milky Way in the past, or when it might flare more dramatically again. We still debate the geometry of its magnetic fields, the efficiency of its accretion flow, the exact role of spin, and the subtle interplay between gravity and plasma at its edge. In other words, the black hole is no longer hidden from us. But it is not finished with us. That may be the most powerful part of this entire story. Science did not end the mystery. It made the mystery sharper. We replaced one large unknown with many smaller, deeper unknowns. We learned enough to say, with confidence, that a supermassive black hole sits at the center of the Milky Way. But the more precisely we describe it, the more we are drawn into the unanswered questions around it. That is the signature of a great cosmic discovery. It does not shrink the universe. It enlarges it. Sagittarius A star teaches us that the universe does not reserve its strangest realities for distant, unreachable corners. One of the most extreme objects known to science lives in our own galaxy. It has been there the entire time, long before human civilization, long before Earth had observers, quietly shaping the inner Milky Way while our species was still learning how to look up. And perhaps that is the final unease the black hole leaves us with. The cosmos is not centered on light. Not really. Light is just what lets us notice things. But beneath the light, behind the dust, under the visible architecture of stars, there are deeper structures, hidden masses, unseen forces, regions where the rules of ordinary life stop applying. Sagittarius A star is one of those regions, a silence at the center, a darkness around which a galaxy turns. We often tell ourselves that knowledge makes the universe safer, but Sagittarius A star suggests something more complicated. Knowledge makes the universe clearer, and sometimes clarity is more unsettling than ignorance. Because now we know what sits at the heart of the Milky Way. We know it is there. We know how massive it is. We know stars race around it. We know light bends at its edge. We know it flickers. We know it has likely been more violent before. We know it may one day become more active again. And we know that every night, above a planet full of people busy with ordinary lives, an entire galaxy is still turning around a darkness most of them will never truly imagine. That is Sagittarius A star. Not the end of the story. Not the end of the questions. Only the point where the questions become impossible to ignore. Because the deeper we looked into the center of the Milky Way, the stranger it became. And somewhere beyond that shadow, beyond the last orbiting light, beyond the event horizon we finally learned to see, the universe is still keeping the rest of the answer to itself.